Okay, and so now if it works, I'm trying to tap. Very good. Okay. If it works, and it seems it works, we can start with the theoretical treatment of the separation of variables. And so next topic is called exactly separation of variables. And when I'm talking about separation of variables, it's a very huge argument again. But for us, separation of variables will be treated in the following case. We consider first order ODE of the form y prime is equal to g of y times h of t. So it is the product of two functions, okay? This is very important. This is the product of two functions a function which is of the y only, and the function of t. These are the two functions. And here we have to follow the steps used for Verhulst equation. What were such steps? And let me recall them. The first step was to find constant solutions namely algebraic solutions, so numbers, constant solutions are numbers, basically, constant functions, to the equation g of y equals 0. Okay, and so here in this graph, in the plane ty, of course, these constant solutions are represented by horizontal lines, like this. This. And here, let me stress one point, remark, due to the theorem of existence and uniqueness, of the solution to a Cauchy problem, of course, under suitable hypothesis, it follows that for any point of the plane, Ty, there is only one solution. For every point there is only one solution. This is extremely important, because if two solutions would cross, and this one here, at the point where they cross, they should solve the same Cauchy problem, okay? Because every point is an initial datum for first order differential equations, okay? As a consequence, there's constant solutions partition the plane in regions. These regions are indeed horizontal stripes, like this, 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 and this in the picture. The plane in regions, horizontal stripes, where any solution is confined. What do I mean? I mean that any solution must be entirely contained in one of those stripes. It means that if the solution starts here, then it must remain here, because if it exits from the stripes, then it meets a constant solution here. But due to the theorem of existence and uniqueness, they cannot cross each other. Two solutions cannot cross each other. So this is the first step, constant solution. Constant solution are found like numerical solution of this equation, g of y is equal to 0. Second, suppose that the function g of y, which is present in the equation, the right-hand side, is different from 0. And this is obvious because this is natural, since we are no longer treating the constant solutions and then divide both members of the equation, both sides of the equation, by g of y. So you have y prime divided by g of y is equal to h of t. Okay? So here the separation of variable, is realized in the sense that in the right-hand side one has y prime and y only, so no explicit t. And in the left, this is in the left-hand side. While in the right-hand side, one has t only, no y nor y prime. Okay, so now we are here, we are at this point, and now we integrate. Third, and let me call it asterisk. So we integrate both sides of asterisk and the variable t. This is very important. This means that you can use the indefinite integral. It is more convenient here. So you have dy, let me write down all the passages. So y prime dt divided by gy equals h of t dt. But now perform the change of variable from t to y and the integral at the left-hand side. And then the important passage is the following: t is replaced by y, and so y prime dt is replaced by dy. Then, and this has to be emphasized, and then you end up with dy g of y, 1 over g of y, is equal to ht dt. And here the separation of variable is complete, and now we can move forward and call capital H and capital G two functions such that capital H is a primitive of H and capital G is a primitive of 1 over G, so be careful here. And then from double asterisk we have capital G of y is equal to h of t plus c, where c is a constant of integration. Now the fourth passage, which is optional, because sometimes it is impossible. Very difficult or even impossible. But explicit y, so from 3 asterisk, which is this one, you have to explicit function y. So y is equal to the inverse of g, capital G applied to g, y, so it is g minus 1 h of t plus g. So it is important to notice the following fact. So after expliciting y, C is no longer an additive constant. So some example. So first, a very trivial example. Malthus equation is of this type. Not only Fairholt, or Malthus. So we have a problem is find all solutions to the equation 1 prime alpha of y. This is an equation of with separate variables. So it is not difficult to integrate. Here we have g of t, h of t is equal to alpha, and g of y is equal to y. So first, constant solutions g of y equal to y is equal to 0, and here is the schema. We already know the it has to be made trivial, and then for non-constant solution we separate the variables and we have dy over y is equal to alpha. This is the integration, so log absolute value of y is alpha t plus c, and then absolute value of y is equal e to the alpha t plus c, so it equal, so we have that y is plus or minus e to the alpha t plus c is equal to plus or minus c e to the alpha t for c larger than 0, so we can say that it is c e to the alpha t for c in R. Just a different way to write it, and so these are the solution for alpha larger than 0, of course. Very easy. So another example. So first, let me give two definitions that are important. There are just names. The first name is general integral. So given an ODE, an ordinary differential equation, the set of all solutions to such ODE is called the general integral or general solutions, general solution, sorry. Such an ODE. Okay, and this is a set. And the other definition, given an ODE, a solution, so any solution to such ODE is called a particular integral or particular solution. To such ODE, to it. So remark, linguistic remark. Here, integral means solution. I would say because to solve an ODE, one has to perform an integration or many integration. One has to integrate one or more time. And moreover, particular, what is the particularity of a particular solution? No particularity. A particular solution has nothing particular. Particular means specific. One solution. And now, let us go to another exercise, which is solve the Cauchy problem y prime is equal to t 1 plus y square, and y of 0 is equal to 0. Solve this Cauchy problem, and here as a first step we find the general integral of the ODE. So g of y, first we notice that g of y is equal to 1 plus y squared. This is a separate variable, and this is always different from 0, so there are no constant solutions. Then, moreover, by separation of variable, we have y prime divided by 1 plus y squared dt is equal to t dt. So here this is equal to dy divided 1 plus y squared. And so we have arctangent of y is equal to t squared over 2 plus c. So y is equal to the tangent of what? T squared over 2 plus c. You may wonder here about the fact that this square over 2 goes to plus infinity as t grows and so on and so on. So there are many asymptotes and so on. So in order to, the point is that in order to remain in the range of the arctangent of y, you have to suitable choose C. This is an interesting discussion, but we will avoid that. When we have this sort of discussion with differential equation, everything goes well, also when you really don't think about that. Then if you want, we can discuss. But here we proceed in a very sloppy and mechanic way. So this is the solution, this is the integral, the general integral. And now we impose the initial condition zero is equal to y of 0 is equal to the tangent of c. So we can use c equal to 0. Of course, we can also use c equal to k pi for every k in z, but it gives exactly the same solution, because the tangent has periodicity equal to pi. Then the function y is equal to the tangent of t squared over 2 is the solution to the Cauchy problem. So here we learn how to solve a Cauchy problem. First we have to pass through the general integral, at least in this example, and then finish. But there is another possibility, example 3, solve the Cauchy problem for instance, y prime is equal to y squared t minus 1, or t squared minus 1, and y of, for instance, 3 is equal to 1. Okay, this is a separate variable, but notice, oh, sorry. So let me, t squared, y squared minus 1. This was my idea. This was my idea. So, notice that here, g of y is equal to y squared minus 1. So y equal to 1 and y equal to minus 1 are constant solutions. So this solution satisfies the initial condition. And now you use the uniqueness. By the uniqueness of solutions, of the solution to a Cauchy problem, by this result of uniqueness, you find that y equal to 1 must be the solution we looked for. So in this very lucky case, you don't have to find the general integral. So in the next video, we will talk to another